Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning. It's a great pleasure this morning to introduce Chenggang Wu from the Institute of Computing Technology in the Chinese Academy of Sciences. Chenggang has received his PhD in computer science from the ICT in 2001, and he's been working on dynamic binary optimization, computer architecture, and virtual machines. And today he's going to be talking about binary translation system for the Loongson processor. Please welcome Chenggang.
Okay, thanks for Ben's introduction. Can you help me? Okay. I cannot hear it.
The microphone is mostly for the recording.
Okay. Because my English is not good, if you cannot understand what I said, you can interrupt me anytime. I'm from the ICT. I focus on the binary translation for about 8 years. Our task is to develop the binary translation system for the China-made processor named the Loongson processor. Now I introduce my work to you. Before I introduce my work, I want to introduce my group. This is all members in my group. We have one faculty, three staffs, and 5 PhD, and others are masters. My research area is dynamic compilation, include binary translation, dynamic optimization, and recently we started research on program reliability. We try to use the dynamic method to find the concurrency bug of the parallel program. We just studied it. We do not do deep research on this area. This is the outline of my presentation. The first one is I want to introduce the requirement of the China-made processors. Another is the second. I will introduce our system named the digital bridger, and introduce some experience and progresses. Loongson processor is developed by ICT, also by ICT or institute, not my group, another group, another lab. They adopt a MIPS-like instruction set. They inherited all the MIPS instruction set and extend some instruction set for binary translation. So they want to support the binary translation very well. But I will introduce what all done. We do not use many of the extension. We do not use. Loongson has developed three generation processors. The first generation is one core single issue, just a simple processor. Then they developed the second generation, 2A, 2B, 2F. They are one core processor, one core for issue processor. Now they are developing 3A and 3B. 3A is 4 cores and 3B is 8 cores. They may develop 16 cores for 3C. The frequency of the processor is not very high, about 800 megahertz to 1 gigahertz. This is the picture of the Loongson processors. Now, let me introduce our system. Because Loongson processor use MIPS instruction, there are little applications of support MIPS machine, so they need us to migrate the x86 applications to Loongson processor. This is the mechanism of the binary translation. We want to migrate x86 applications into Loongson processor and use our virtual machine to support it. Let me introduce our progress. The performance of our binary translation system is 67% of the native performance. How we get this data? The methodology is we generate Spec 2006 benchmark, use GCC 03 flag to generate the code, then use our binary translator system to run on Loongson and get the performance data. Then we use the native GCC with 03 to generate the native code. Then we compare them, we get the data. Our system now can support Adobe Flash Player, Adobe Reader, and Apache and MySQL. These real applications. Only Adobe Flash Player is not available in Loongson processor. So this is the main contribution we made to Loongson. Let me show. This is the performance data. Let me show you the experience of the user experience of our system. We according to the requirement of Adobe, they require Pentium 2 with 800 megahertz, and the Loongson 2F also have this kind of frequency. So this is the minimum hardware requirement. Let me show you the. Because the speed of the binary translation is most important, so I show you the user experience. This song, I think some of them may listen this song in the Olympic opening ceremony. This is the result. We can have this kind of user experience. This is for the videos, and for the animation, it can be better. So it is better than the video. Okay. Let me continue. So to get the good performance, let me introduce my experience. The most important thing for us, we found to improve the performance is not the new technology. It is just from the select the target machine instruction to simulate the guest instruction elaborately. This is the most important thing. We do this work. It is engineering work, but it can get good performance. After we do it, we can get the performance can reach 40% of the native code, 40%. So it is very useful. Then my second experience is to leverage the local resource as much as possible. If we can use the local library, if the system have local library, we just use it. We do not translate it, because the local library have much have better performance than the translator performance. And we use the local software frame. For the Flash player, it is a plug-in of the browser. The browser, we try to translate the browser and the plug-in together, but the performance is not good. So we only translate the browser, not browser, plug-in, and we use the local browser, so it can get good performance. These two aspects are our experience. I think we need not to introduce them in detail. I think it is very simple, but it is include a lot of engineering tasks. For the progress, I think we have 4 important technology. First one is to handling misalignment data access efficiently. It is published in CGO 2009, and then improve the data locality by pore allocation, published in CGO 2010, and then improve the data locality by on-the-fly structure splitting, published in HiPeak this year, and promote local variables into registers, published in CGO 2011. So the following, I will introduce these 4 techniques. For the first one, because x86 the hardware support misalignment data access, it will not introduce big overhead. So the compiler do not turn on the alignment operation. So there are a lot of misalignment in the program, in the binary. The misalignment will introduce greater overhead. What is the misalignment? I think I need not to introduce it, because you are experts. So I think I need not to introduce them. But for the modern RISC machines, especially on Alpha and MIPS, they do not have this kind of support. When the machine, when the processor run on misalignment access, it will trigger an exception. The cost of the exception will be 1,000 cycles, 1,000 instructions. So the cost is very high. This is the statistic data for SPEC 2000 and 2006. We found for average there is 1.44 misalignment data access in the program. But for some programs like ER and some others, and art and some others, the misalignment will be very high. So it will introduce much more overhead. Before we...
Can you just ask about that? that your program is originally compiled with GCC?
Yeah.
Is that right? So does the compiler itself try to avoid misaligned accesses when it?
The compiler can deal with the misalignment data access, but the option do not turn on.
Okay.
For the O3 option, it is not turned on.
I see. So you're just assuming that people won't do that optimization?
We assume people do not do that. But indeed, the real applications, in real application, it is not turned on.
Right.
Yeah. There exists a lot of misalignment data access. So there also already exists some method, one method called direct method. This method is used in virtual machine named QEMU. In this virtual machine, it handles it when it meets misalignment data access. It will translate it with a sequence of code. This code do not trigger misalignment, but it will introduce much more overhead than a single instruction. For QEMU, they translate all of the data access instruction into this kind of code sequence. So for some data access instruction without misalignment data access, it will introduce the great overhead. This is another method named static profiling. This method is used in FX32 system. They execute the application, and they instrument the application and execute it, and get the misalignment information for the instructions. Then they, when they translate the system, the application, they only translate the instructions with misalignment they found. But for this method, we found for different input, the misalignment will be different. The instruction will be different. So it is not a good solution. This method cannot make adaptive. So, okay.
So obviously your results from the profile are that you can't prove that something will not, that a location will not have a misalignment. So
you're right.
Exception in that case.
Yeah.
So it still works. It just has it has the really expensive solution at one time.
Yeah. For some input, some instruction will trigger misalignment access, but when use another input, other instruction will trigger misalignment. But this instruction found by the profiling do not trigger misalignment.
Right.
Yeah.
The profiler thinks it won't.
Yeah. So this is a method that we call dynamic profiling. This method is used in IA32 execution layer developed by Intel Shanghai. This method, they use an interpreter to interpret the program. When they use an interpreter or use the instrumentation method. For IA32 execution layer, they instrument the binary code. When they found some in the loop iteration, in the first 10 or 20 execution iteration, they found this instruction trigger misalignment access. They will translate this code into the sequence code. This method can work very well for some applications, but we found for some there exists some application. The iteration of the loop exceed how much I forgot it. Let me try. Yeah, for this application, it need 266 iteration can trigger the first misalignment data access. After it will access the misalignment data frequently. So this method cannot work very well. So we propose another method named exception handling. It is very simple. We use the translator to translate the translator XZ6 code into MIPS image. Then, before translation, we will register exception handler. When the code triggers the exception, triggers the misalignment, it will trigger the online exception. This handler will modify the code according to the information we get. We have also do some optimization. For us, if we use the exception handler to patch the code, it will destroy the code locality. So we do code rearrange the code to move this code down and move the code upward to improve the code locality. And we combine the dynamic profiling method with our method together. We use an interpreter to interpret the iteration several times to find some misalignment data access and translate them into the code, the code we want. And we use our exception handler to find the misalignment we do not find during the profiling time. And we do another optimization. We found in a basic block there are a lot of misalignment. We will translate them together without instead of translate one instruction each other to improve the code locality. And for some code, we use multi-version to check. We generate the code to check if this instruction will trigger misalignment. And according to the check, we use the original instruction or use our misalignment data access sequence. Very simple method, but it is very useful. It increases our system 20% performance. It for our system compared to other three methods, we can achieve 21% better than dynamic profiling, 14% than static profiling, and 76% than direct method. Okay.
So, do you have a measure of how much it increases the size of the code? Because you're adding.
We do not, because we do not. I forgot the exact data. Because these people have published several years ago, I do not remember the data. It is not very, very high. Okay. We can calculate from the instructions. For one instruction, for this is the instruction with misalignment data access. For one instruction, we will generate 7 to 11 instruction for one instruction. So we can multiply this with them. very small. Another progress is improve the data locality by pore allocation. Dynamic heap memory allocation is widely used in modern programs, but the general purpose heap allocator focus more on runtime overhead and memory utilization. They do not focus on the data locality. Let me give the example. Suppose there are 3 data structures. One is a list, another list, and a tree. The programmer writes the code according to their purpose, so it may access, the program may access one node for list 1, then for list 2, then for tree, for list 2, for tree, and so on. So this layout have poor data locality. So we use the pore allocation to aggregate heap objects into separate memory pores at the time of their allocation. We set 3 pores for this one. When the program runs, we let the allocation for list 1 to allocate in these pores. For list 2 to allocate in this pores, and for trees in this pore. So it can improve the data locality, because the program when the program access the data structure, they always access with this sequence. How to do it? Before we do this work, there exists another work. They use the allocation set to allocate the data. And when they found in this allocated set, they design a pore, they set a pore, and let the data allocated in this set to set this pore. So they use different sets to set different pores. But sometimes there exist some problems. For I think you know, for the modern programmers, they always use the wrapper, like this code in TWOF. They use shift malloc. In this function, they call the system function, library function malloc in this set. If it can malloc data from the heap, it will return a pointer. If not, it will return a no pointer. For TWOF benchmark, all data allocated by this wrapper. So it will introduce a problem. If we use this allocation set, we will allocate all of the data into one pore. So this is a problem. This is another application also have this kind of problem. However, for this is the example have this problem. So our solution is to use the call chain, but we found that we have three kind of selection. The first one is use the full call chain from the allocation side to the main function. But the call chain is very long. It will introduce much more overhead. If it in a recursive method, the overhead will much more worse. Another choice is use the fixed length of call chain. We can use two call chain, but for this application, some wrappers have several layers, or not one layer, so it cannot work very well. We design adaptive partial call chain. We analyze the code of the binary and try to find if it is a wrapper. If it is a wrapper, we will to enlarge the call chain, so it can work very well. For some data, different allocation set may allocate the data for one data structure. This allocation this allocation set and this allocation set allocate different node, but the node will connect together to form a data structure. So this problem we must to solve. To solve this problem, we design two affinity named type 1 and type 2. The type 1 affinity means the object, if the object have the same type and they linked together, so we assume they have the type 1 affinity. Just like this, they have the same type and connected together by the point. So this is the first, the type 1 affinity. The type 2 affinity means for this node, they do not connect each other, but they are connected by the type 1 affinity nodes with the same field. So we assume they have the affinity. So we use pole 1 to put them together, you put 2 to put this kind of node together. When we found, suppose this node and this node do not allocate in the same set, we will combine them together. We'll merging them together. To publish this paper, we okay.
So can you go back? So is this done statically? Are you
dynamically?
Dynamically. Okay.
Yeah.
So
in the runtime.
How do you know that is it type 1 or type 2? What test do you do?
We do not know the type. We can what we know is the size allocated.
Okay.
But if the size are always the same, we believe we assume they have the same type.
No, but how do you put them in pool 1, pool 2?
How
do you decide which pool to put them in?
If we set in the first when we allocate this node, we do not we try to find if any others have the same affinity. If it is affinity to some others already exist.
Based on the linking.
Based on the linking.
So how do you monitor that?
How do I?
You do that dynamically. You determine that dynamically.
Yeah. In the beginning, there is no pool.
I know.
We set one pool. We only set one pool. So when the program allocated the first node, we put it in this pool. When it allocated another node, we will compare if it, we will compare if it have the affinity with the existing node. If it affinity with the existing node, we will allocate it in this pool. If not, we will allocate another pool and we will allocate another pool and allocate the node in this pool.
Right, but if you don't have type information, how do you know? So what is that affinity? What is the dynamic test you do?
What?
What is the test? The affinity test.
Affinity test.
What is it? What do you check?
We check two things, two attributes. One is the size.
Right.
We do not know the type. We know the size.
Right.
We can check it if they have the same size.
Right.
The first one. The second one, we check if it have a point from this one to point to this one. We check it.
How can you check that if you're allocating the second object? There are no pointers into it or out of it, right? There's no
When it allocates it, the function must return an address to a register. The register, the value of the register must assign to exist variable or exist.
Yes, but what he's asking is how do you know whether there's a pointer between the two? How do you know there's a pointer between the two?
Oh, I see. For this wrapper, it return address, but in this code, the address will be returned to its caller. Now, for its caller, we will check the code and to find.
You anticipate where it's going to be stored.
What?
You anticipate where it's going to be stored by doing a program analysis.
Yeah.
You find out which field it's going to be stored in.
Yeah.
So that's a static analysis before.
We do not do static analysis.
And how do you? I mean, you need to know knowledge when you do the allocation.
When it allocates data, we start the analysis. Analysis is the binary. We try to find which instruction do this task to assign the return address, this address to a pointer.
So basically, you look at the instruction that follows the call.
Yeah. We look at the instruction that follows the call. Yes.
Dynamically.
In the runtime, on the fly. But we do not
static in a sense because you're doing it at runtime, but you're doing it before you run that code, right?
Not before, after we do it.
Yeah, but you've already allocated it, so you can't move it from one pool to another once you've
We do not move.
Right, so you need to know before you allocate. Which
we catch the allocate. We do not allocate the data. We do not allocate the data. Just when we found the code assigned the pointer to assigned the address to a pointer.
You delay the allocation
Because we use all allocator. We interrupt this allocator. Sure. We do not let it allocate the data. We do not let it allocate the data. We intercept it. We intercept it, and we delay it.
You delay it. Okay,
Yeah.
That's the trick.
We delay it.
So you wait till you know where it's stored, and then you allocate.
Yeah.
Okay.
But we only do it one time. We do not because this allocation set may allocate 1 million times. We only do one time.
Oh, and that's based on the call stack that we're
Yeah. If the call stack change, we do another time. If it does not change, we only do one time.
Nice. Thanks.
Because we want to publish the paper, so we do our experiment on x86 machine, not on our binary translation system, but we use it in our system. We test it on two machines. One is Intel Pentium 4 and Intel Xeon. My pronunciation is right? Xeon. The difference between them are level 2 cache. The level 2 cache for this one is very small. For this one is bigger. The main difference for it, we choose the 12 benchmarks from SPEC 2000-2006. The policy is when we found the used memory used in pulse divided by the memory used in heap is larger than 1%. We choose this kind of benchmarks. For some benchmarks, we can get the great improvement. For this one, in the second platform, we can get 80% speed up. For this one, in the first machine, we can get 50% speed up. The main reason for the speed up are different. For this one, we can the performance come from the we reduce the TLB miss. We reduce the TLB miss greatly. For this one, we reduce the catch miss greatly.
One question. So can you use this for? This is in the context of this binary translation.
Yeah.
But does it have to be? I mean, it seems like pool allocation is useful for any program, right? But
for any program.
To apply your technique if you're not translating because of your tricks of delaying the allocation. Is that the reason why you're doing it? But you're not
I'm not sure.
It's a general technique, right?
Do you mean can I use this technique for other?
Yes, optimizing an existing allocator, some other allocator.
I think it can, but for some program it cannot get performance gain. If the workload is very large or very small, it cannot get the performance gain. If the very large, we cannot reduce because for some applications the workload is very large. No matter how we reduce, we improve the locality, the catch miss and the TLB miss will be great. So for the small application, for the workload, for the application with small workload, it cannot work well. But for some applications, before we optimize it trigger catch miss and the TLB miss. After we optimize wait a minute. After we optimize it, the workload can fit in the cache. It can get greater performance again. Yeah.
So really quickly, just to follow up on that, can you go back to the slide that has the results? So what's your baseline here? Because this is on the Intel hardware. So are you doing the binary translation to GCC, for instance?
I forgot it because I forgot it. GCC or ICC, I forgot it.
Okay.
With the hardest optimization option, but I forgot it.
So then
I can check the paper.
Are you writing out x86 when you do the DPA?
Yeah.
Do you write out x86 or do you write out? So how do you actually implement this at runtime?
We rewrite x86, not MIPS. Yeah. But we implement in our system.
Yes.
Yeah.
But as you said, you could probably do this statically once per call site, per call to malloc.
Per call site statically. It can work, but it cannot not work well due to the same allocation set may allocate a different data structure. Yeah.
So have you looked at inlining? I mean, these wrapper functions are pretty small generally. Yeah. You can imagine just inlining all the wrappers, and that would eliminate.
Inlining wrapper. I remember it is not a problem. We already discussed it before we published the paper. Inlining. No, it is not a problem. When it inlining the wrapper, the call set can work well.
Mm-hmm. Right. So that would save overhead to measure the. I mean, you could.
We do not, from the binary code, we do not know. We cannot identify which code is in line.
Right, I understand. Yeah. Right. Okay. So I was suggesting if you actually had the source.
Yeah.
And you inline the wrappers.
Yeah.
Right. Then you wouldn't have this. You wouldn't have to go up multiple frames in the call stack.
Yeah.
And it would save you the effort to do that. And then you could do a static analysis at every call site, which is what Todd is suggesting.
Yeah.
And you wouldn't need to do the dynamic analysis.
I'm sorry, I do not catch you. What do you?
Okay, so it's not bad. We can talk afterward. It's okay.
We can talk. Okay.
Yeah.
My English is.
No, it's okay. Yeah.
Yeah, we discussed the inlining. It can work very well by the call set. Yeah. This is the third method. The second method, the third method. This is the second method. The second method is improve the data located by line on-the-fly structure splitting. We always do the optimization on the fly. So the memory wall has long been a main barrier that limits system performance. Data layout. Many technologies have been proposed to improve the data layout, such as structure splitting, field reordering. But this kind of technology has some problems. This kind of technology can improve the performance for many applications, but for some applications, they can slow down them. I will show the data in the following slides. And for this kind of optimization is not very safe, so it needs the check runtime carefully. Otherwise, we'll introduce the bug in the system. So this method have not been applied in many compilers for performance and safety concerns. We designed on-the-fly and a dynamic on-the-fly approach to apply the data structure splitting optimization. Need I introduce structure splitting? Do I need to introduce what is structure? No, I think no. Okay. This is the framework of our system. This is the origin, the binary code, program code, and this side are our system. When the program running, it may allocate data. We intercept the allocation request. Then we catch the allocation. We use our allocator. Our allocator include a large array allocator and the object pool allocator. When we found a large array and a large object pool, this object pool I just introduced in just now. When we found these two kind of data, we will use them as our optimization candidate. The allocator The allocator will invoke the analyzer to do pointer analysis to find the possible access instruction to the allocated data, and to try to recognize the size of the structure and the fields of the data, and to do benefit estimation. If the result shows we can get the benefit, we will allocate two spaces, two blocks of spaces. One is the original space 8. After we allocate it, we protect it. We do page protect with non-readable and non-readable flag. And in the same time, we allocate another space. We name it splitting space to use it to store the split data. Because this kind of data is page protected, when the PAI access the data, it will trigger an exception. So all exception catch it, and we generate the exception handler. Will introduce the analyzer another time. The difference is it has the runtime information of the variable of the register, so it can handle this kind of information and to generate the code. We replace the original PAI pointer, original possible access instruction. We replace them and let them to access the splitting data. So we patch the code. We put the code into the code cache and patch it into the program code. Afterward, the program can run without trigger the exception.
So doesn't seem safe. In
Yeah.
case of forced polymorphism.
You are right. I will introduce the same guarantee mechanism. Yeah, the safe is very important for this optimization. Yeah. When we also designed a rollback module. We found some violation of optimization. We will do rollback to solve the safety problem. And we set a monitor to monitor the pass counter. When we generate the code, we will instrument the code to record the loop iteration, the times of the loop iteration. The monitor will check it. If we found it is not, the optimization is not efficient, we will do rollback. Okay, let me introduce the analyzer first. The analyzer do 4 jobs. The first one is find the PAI, possibly accessing instructions. If EAX is calculated from the allocation set, from allocation address or the return address, these 3 instructions are PAI. But an important issue is how do we find EAX, the relationship between EAX and the call set. We can use 2 technologies. One is point-to-analysis. the point to analysis is very difficult for static compiler. Although the static compiler have the original the source code, so it is much more difficult for us because we do not have source code. And in the binary code, there are a lot of indirect register addressing mode in the binary. So we design another lightweight flow-sensitive propagation method. We just propagate the address according to the control flow. If we found it is they have the relationship, we recognize this instruction is a PAI. This method can find some PAI, but for some others they cannot find. The undiscovered PAI will be found by our safety mechanism. Another task is recognize the fields. For this task, it have two tasks. One is getting the structure side, another is getting the field offside and the side. For the structure size, we assume all the PAI always access the same field. But this assumption is not always true. It's not always true. We must check. We have a mechanism to check it. We assume it. So under this premise, we getting the stride of PAI of our loops and calculate the greatest common divisors of the strides. We assume these results are the structure side. It may be the multiple of the structure side, but it may multiple, but it did not influence or affect our optimization. Another task is to get the field size and offset. It is very simple. Suppose EAX is the start of the allocate space is the start. So the field at the offset 4 is 4 bytes from this instruction. We can get other information. We do estimate the benefit. We use a heuristic method. It's very simple. We only calculate the field coverage. S is the structure size. T is the structure's number of bytes touched by the loop or trace. We believe if field coverage, the smaller the field coverage, the better for us. Yeah. Another job is the allocate memory. For some data, if we found not beneficial, we will allocate them use the default allocator of the system. For others, we allocate the original space and the splitting space. For the exception handler, it generates code. We use this equation to calculate the offset, and use this equation to calculate the new address of the splitting space. So we generate instruction. We generate instruction like this. For one PAI, original PAI, we will generate instruction like this slide. First, for the safety, first we check if P is the pointer, original pointer. If P is in optimized space, if not, we will let it to execute the original PI. Do not execute all PI. Another one is to check the offset. I just assumed every PI access the same field, but it is not always true. So we use the code to check it. If it is not true, we will do rollback.
So do you use a different optimized space for every type of allocation to do every pool?
What?
Is there a different optimized space for every different memory pool?
If we estimate we can get the benefit, we use it. If not, we do not use it.
So I'm thinking about the case where you can have two different optimizations that clash.
Two different
so
optimizations.
You can be an optimized space, but you can be a different kind of object that you can split differently. That is driving at this course.
I'm sorry. What do you mean?
So that check doesn't seem...
No, which one? This one?
The first one.
Okay. Does seem
it's
what?
Not clear that it catches all possible things that can go wrong. It doesn't seem safe enough.
Why? Why it doesn't safe?
So if at the field access site,
yeah,
if it's polymorphic and you have different.
You mean? I know what you mean. You mean if there exists some point PAI to access the optimized code, optimized space, it will be wrong. Do you mean?
If there are two optimizations, different optimizations.
Two different optimizations.
That arrive at the same.
One is all, another. What is another? Two different optimizations.
Well, so objects are allocated in different places, different call sites, but then they get passed to this routine where it accesses the object.
Oh, you mean this routine may access this part of data and this part of data? Am I right?
No.
Why don't we do it offline?
What does this?
We can talk afterward. It's a little complicated. I think you need an example to try to.
I'm sorry. No. I think I must improve my English. I listen. I study English every 2 hours of one per day, but I think I should improve my English. Okay, after the talk, we can discuss it or use the paper. You can draw the problem to me, okay? Okay, for the optimization, we use 22 instructions to replace one PI. It's the overhead. So we use several means to reduce the overhead. First one, we use the Leibniz analysis of the register. If we found some registers are not used in this time, we use it. So it can reduce the instruction. We optimize by the sequence PI. If we find several PIs, we optimize them. Use the same check. And we do stress reduction and do code promotion. Code promotion means we promote some code outside the loop, some code outside loop. Okay. Then we do persistent profiling. We set a monitor here. We do persistent profiling. We use a matrix named ratio to calculate. We calculate the penalty cycles and the reduction of catch line touches. For 8, we calculate. We just estimate. We do not we just estimate. We estimate use the number and the complexity of the instructions. We count the instructions, and for some instruction like divided instruction, we think the overhead is high. We check whether this instruction can be promoted outside the loop. And we use the field coverage at this F to do the calculation. When optimize is not effective, or there exists a field violation, like in C programs, use union or use the typecast. For this problem, we will do rollback. And the other cases that our system cannot handle, we will do rollback. The rollback is very simple. We restore read and write privilege of the original space and merge the splitting space together and move the data to the original space and free the splitting space. For the safety problem, I'm not sure if this slide can answer your question. For the original instruction, if they access the unoptimized data, it is good. It is the original behavior of the program, so no problem. For the original instruction, if they access the optimized data, because these data are page protected, so this instruction will be captured by exception handler and transformed into PAI or optimized code. So no problem. And for the translated instruction access the optimized data, if there is not field violation, and PAI always access the same field, no problem. But if these two conditions do not if there exists a violation, we'll do rollback. For the translated instruction, if they access the will access the unoptimized data, we will check the addresses and let it to execute the original PI rather than our PI. So no safety problem. This is the speed up. We realize our optimization and test all the benchmarks. But we only find 5 benchmarks trigger the optimization. For other benchmarks, no speed up, no slow down. For this program, it can achieve the speed up, and this achieves speed up. But for this one, slow down. I should introduce the 3 bar. The red bar is the allocation method. I just introduced. The green bar is our method without the monitor, to monitor without the monitor. And this one is our method with the monitor. So without the monitor, it will slow down for this benchmark. The reason is this benchmark do not access the data sequentially. It accesses the data randomly. So it triggers slowdown. With the monitor, we found no performance gain. We roll back, so no slowdown. I think the speed up of 0.9 maybe the inaccuracy, maybe. So for this one, no slowdown. So it also prove this optimization. If we use it statically, it cannot work very well, because no monitor to roll back. Yeah.
So historically, I think many of the papers that try to do this have a similar result. Like
yeah.
Basically, it only works for certain programs, and and there's costs.
Yeah.
So, given your experience, would you actually recommend implementing this optimization? Now that you've done all the work and you've seen the results.
With done a lot of other work, already published work. Do you mean?
Well, I was going to say, just based on your results here.
Yeah.
So would you recommend that other people implement this optimization, or do you consider it not a good enough result? It's not enough of a benefit.
But I think the benefit for some application like art, it is very high. It is useful. So we found in the static compiler in GCC 4.4 there exists this kind of optimization. Yeah, but it is not turned on always. It is not turned on. I think the reason is for some benchmarks, it will introduce greater overhead to slow down. So, but for all methods, we do not introduce a slowdown.
Right.
Yeah. Yeah.
So some of the reasons that it may not work well is that the x86 processor is very good at prefetching data for you, right? It does a good job, so it's hiding some of the latency issues that you run into. But it seems like a simpler processor that might be in order, like one of your earlier versions of the Loongson processor. This might have a huge benefit. So do you have the same graph for
the earlier
is an in-order processor?
No, we only do it in the new processor. Oh, the last one is promote local variable. Do I have time?
Not much.
Not much.
About 5 minutes.
5 minutes. Oh, okay. The last one is promote local variable into registers. Because x86, we translate x86 into MIPS. MIPS have 32 local general purpose register, and x86 only have 8. So if we for x86 because there are due to the reason they must do register spill. They must spill register when they allocate the register. So when we translate, we try to promote the local variable into the register to reduce the overhead. So since I do not have enough time, our method is for these yellow instructions. We found. We do all this work on Intel 64 platform, not on MIPS. The reason is it is easy to publish the paper. So for these 3 instructions, we found this instruction access this data, this stack data. So for Intel 64. They have 8 extra registers, so we can use them to do preload and do restore. So in the loop, we can replace the stack variable by the new registers. This optimization is simple, but the most important thing is how to guarantee the safety. Okay, now time. The main reason is why we target stack variable, because it is simple than other variables. The reason is it is explicitly referenced. It is relatively easy to disambiguate explicit reference. But the one safety issue is how to detect the memory alias. We use memory unprotected to do this job. When we promote the stack variable from this page, we will protect it and promote the variable outside. But this method will introduce another issue. For some data, because we do not have enough registers to promote all the local variable. So the other variable, how do we handle them? Okay. The solution is we use mremap to remap a shadow stack. We we retarget the explicit memory access instruction into the stack, shadow stack. These two part memory share the same physical memory, so we change them to the shadow stack, so the problem can be solved. But there exist some other problems. For the original static stack, it does not permit mremap operation. So we must allocate an image stack first and transfer the stack pointer into this stack and do remap. Only 5 minutes. I think I have run out of the time. Okay. So let me show the result for the application. For some application, we can achieve 45% speed up. For the average, we can achieve 7.3%. Okay. I'm sorry, my poor English, I cannot explain.
You had a lot of great material. Any further questions? So Chenggang is going to be with us for the day, and he's going to join me with lunch. If you want to come to lunch with us, you're welcome to. And we could probably find some room in a schedule later if you want to talk to him. So just let me know.